Okay, so we've done a lot of calculations for number fields, how to compute their discriminants, how to compute the norms and the traces of elements and so on. So now let's look at a wide range of examples. This is like a very interesting class of number fields, which have lots of importance to number theory. And this is out of cyclotomic fields. And cyclotomic fields, the word that you should think of what you should think of with cyclotomic fields is roots of unity. So it's a field that you get by just adjoining lots of roots of unity. So these are some of the more interesting ones. Let me just do like a vague remark. So cyclotomic fields are ones of the form, say, Q zeta n, where zeta n is whenever I write zeta n, I'm going to mean primitive. So nth root of unity. So it has order. Primitive just basically means the first time that the first power at which it becomes 1 is n. There's no smaller power at which it becomes n. So this is what these cyclotomic fields look like. So for n equals p, a prime, we know that. So we know that x to the n, well, x to the p minus 1 is not irreducible. We saw this in one of the examples, but we denoted phi of p, which is 1 plus x to the p minus 1, is irreducible. So, and the roots of this thing, so this is what you get when you divide this polynomial by x minus 1. The roots of this are the roots of unity that we care about. So here's a result about the minimal polynomials of roots of unity, which I'm not going to prove. We'll just use this. You may have seen this in Galois theory, I don't know, or in some other course, maybe in the number theory course last time. It says for any integer n, phi of n, so this is the minimal polynomial of zeta n, has degree phi of n, where phi is the usual Euler totient function, where phi is Euler's totient function. So you'll remember this from the number theory course. The number of prime, phi of n is the number of how many numbers less than n are co-prime to n, sort of thing. So I've not told you how to find the minimal polynomial of a general nth root of unity, but I've told you what the degree is. And here's a theorem which tells us a lot about what these the number fields look like. So here's theorem 2.3.2. Let zeta p be a pth root of unity. When I put p, I always mean a prime. But maybe I'll be careful here. Pth root of unity for p an odd prime. So not 2, just because p equals 2 is somewhat trivial. And I'm going to let lambda p be 1 minus zeta p. And I'm going to let k be the resulting number field. So let me tell you something about this field. Then what can we figure out? Well, we can figure out the ring of integers of this is nothing but z adjoin zeta p. This is actually the same thing as z adjoin lambda p. And moreover, the discriminant of the power basis that you choose, so zeta p minus 1. This discriminant, okay, it's the same thing as a discriminant of the following thing, which is again a basis with lambdas, lambda p minus 1. and this is minus 1 to the p minus 1 over 2 times p to the p minus 2. Okay, great. So basically this theorem tells you everything, well, tells you a lot about what cyclotomic fields look like, and we're going to revisit cyclotomic fields later on, but for now this will be a nice family of examples to keep in mind. So proof of this theorem. First note that by this lemma that I just gave you, first note that phi of p has degree p minus 1, so the degree of this field extension is p minus 1. Since we have this relation z to p is 1 minus lambda p, we get that these rings that they generate are the same. Take an element in this ring, change z to p for 1 minus alpha p, and then now you clearly ended up with an element in here. So you get one containment and just do the same thing. You get double just do double inclusion. I'll give you this. So next, I'm gonna let, what notation did I choose? I chose alpha I to be sigma I of z to p, denote the conjugates of z to p under the embeddings I from k into the complex numbers. So I remember that an embedding will send a root to its conjugate. So by going through all the embeddings, I can go through all the conjugates of a root. So these are all the other roots of unity of order p. Now let's use one of our previous propositions. Now by proposition 2.2.17, we have, so this was a proposition that told us about discriminants of power bases. So we have a discriminant of 1, z to p to the p minus 1. This thing was the product of I less than j of alpha I minus alpha j squared. And I'm just going to rewrite this. I'm going to write this as the product over I less than j of 1 minus alpha I in brackets minus 1 minus alpha j all squared. Just put ones on both sides. And then now, if alpha I is a conjugate of z to p, 1 minus alpha I is going to be a conjugate of lambda p. It's because of this relation here. If you apply sigma, the embedding to this thing, you'll see how it works. So this again, by just using the formula in reverse, so we get the discriminant of this is the same thing as the discriminant of this. Okay, so that's maybe the first part. So how do we work out what the discriminant? We know that these two discriminants of these two different bases are the same, but how do we work out what the discriminant is? By proposition 2.2.19, now we have the discriminant of 1 z to p p minus 1. This is minus 1 p minus 1 p minus 2 over 2 times the norm from k to q of, so you take the minimal polynomial, differentiate, and evaluate at z to p. Great. Since the prime number p is odd, figure out this term is just minus 1 to the p minus 1. So since p is odd, minus 1 to the p minus 1 times p minus 2 over 2, the same thing as minus 1 to the p minus 1 over 2. Great. Next, you see that 5p primed of x is equals p times x to the p minus 1, x minus 1 minus x to the p minus 1 all over x minus 1 squared. Remember just that, 5p of x is just x to the p minus 1 over x minus 1. Then you expand it out. So if you just differentiate this expression, you get this expression here. Therefore, by p theta, if you evaluate this at zeta p, you get minus 1 to the p, zeta p to the p minus 1, all divided by lambda p. And 1 minus zeta p at the bottom, so that's just a lambda p. Lastly, note that the norm from k to q of zeta p is 1, since zeta p is a root of, well, it's a unit, so it's going to mean that it has norm 1. But if you think of what the minimal polynomial is, the norm is going to be the coefficient of the constant term, in which case it's 1. Yeah, so since this is the constant term in the min poly, and the signs work out correctly. So usually you have to work out what the sign is, but in this case it is exactly that. So similarly, from one of the computations, we've done in one of the previous examples, from the computation, so from this example 1.2.16, we see that the norm k over q of lambda p equals p. So remember when we checked that this 5p was an irreducible polynomial, what we did was we evaluated this polynomial at x plus 1, expanded it all out, and then you notice that a bunch of p's showed up in the coefficients and so on. And we noticed that the last term was p. If you evaluate 5p at x plus 1 and look at that polynomial, that is the polynomial which lambda p satisfies. And now if I want to know the norm of that, it's just the coefficient of the constant term, which is p, so which gives us this. So if we put it all together, so combining, we get the norm k to q of 5p primed of zeta p. This is the same thing as, I'm just going to use this expression here. So this is the norm of p, the norm k to q. So the minus 1 disappears because the degree of my field is even. It'll just pop out. This to the p minus 1 all over norm from k to q minus lambda p. Oh, maybe I'll just get the sign in the bottom. Yeah, fine, I put the sign in the bottom. But it's going to disappear. Now this is now minus 1 to the p minus 1, which is this, this minus 1 pops out and you get here, and then you get p to the p minus 2, because this term here is just a 1. You just have this contribution from the this has norm p, and this is the norm. Oh, this is the norm k to q of just the prime p. So this has, you're gonna get a p to the p minus 1 from this term. It's gonna cancel out with one of the p's here, and then you're left with a bunch of minus 1s. Great. Which again, in this case, this is just p to the p minus 2 because p minus 1 is even. I have to get off prime. So okay, we know what a discriminant is. So the last thing we need to do. So lastly, we need to check that that what the ring of integers is. I'm going to check that this is zeta p. From above, we know from this calculation we just done, the only prime which divides a discriminant more than once is p. So from above, we know that the only prime dividing the discriminant is p. So yeah, so by lemma 2.2.7, we need to check at P if we have an integral basis. But by lemma, the other lemma, which was that we were using in tandem, 2.2.21, we know that since our minimal polynomial is Eisenstein at P, you know, for lambda P, well, maybe I should. So we need to check that this thing equals this, which equals, we've already seen this bit. So now the minimal polynomial of lambda P is Eisenstein at P. So I'm applying all of this to this thing, and because it's Eisenstein at P, lemma 2.21, we know that dividing by P won't give new algebraic integer, well, new integral elements. So we can't replace anything in our basis by by dividing by P. So this must be an integral basis. And we're done. Great. So we now know for a cyclotomic field the discriminant, what the ring of integers is, and I guess a degree of the field. If you look through the lecture notes, you'll see an extended exercise there if you want to, instead of just doing this for prime P, for prime powers. And then if you combine it with some more exercises that are there, you can end up proving the following. So say if one works harder, so all the exercises that you need to do this, I think, are in the notes to finish it off. But if one works harder, one can show, and we'll use this theorem later on. So this is theorem 2.3.4. So if we just let n be any positive integer, and zeta n and nth root of unity, so then if k is q zeta n, then OK is just this field z adjoined zeta n. So this works not just for primes, not for just for prime powers, but for any n. And we'll use this theorem, but I'm not going to prove it. So proof, do all the exercises in the notes. If you do all the exercises and somehow combine them together, you'll be able to prove this to get this result. Okay, so this is like the first taste of cyclotomic fields. This will give us some nice, interesting examples to work with. Now we don't have to just work with quadratics or cubics. In general, if I give you a degree 10 extension or something, it might be hard to figure out the number, the discriminant, and then figuring out the ring of integers might be really difficult. But at least for these ones, we can get extensions which are of arbitrarily large degrees, but we'll always know what a discriminant and the ring of integers is, and this will be useful for us in the next chapter. So this ends chapter 2, and next we'll move on to studying these rings of integers and the ideals in them. Okay, so I'll stop.